excited to learn Sir Acuña's philosophical analysis, Unit 3, Modules 2 to 7 with you today. It's going to be so much fun. In our former discussions, we have learned about the difference between a sentence and a statement. Statements are the ones that have a truth value which is either true or false. In this part of our discussion, I will be sharing with you Sir Acuña's Module 2 of Unit 3 entitled Representing Compounding Statements. Statements can be classified into two, simple and compound. And here, I will teach you how to represent them. So we have a convention for representing statements and logical constants. And learning the skill of representing statements is our first step in our study of valid and invalid argument forms. A simple statement can be represented by a single capital letter, and it does not contain any connecting word such as either or, and, if then, and if and only if. These words are what we call the logical constants. To explain, the logical constant and is what we call a conjunction, and it is represented by the symbol. The logical constant either and or is what we call an alternation, and it is represented by small letter v. The logical constant if then is what we call the conditional, and this is represented with an arrow. The last logical constant is the connecting word if and only if, and this is represented with three horizontal lines, thus being called biconditional. Now that we know how to represent logical constants, let us now differentiate simple statements from compound statements. Simple statements are statements containing no connecting word. There are no logical constants found in these type of statements. It can be represented by a single capital letter. For example, the statement, sisters are female siblings, can be represented by any of the 26 letters from the English alphabet. We can represent this statement as capital letter S. Thus, the content disappears when we represent a simple statement with a capital letter. Compound statements, on the other hand, are composed of two or more statements. These statements are connected using logical constants. For example, the statement, Christine is a girl, can be represented as capital letter C. Let us now add one more statement saying, Carol is a girl, which is represented by capital letter K. We can join these two statements by conjunction with this symbol. This is read as, Christine is a girl and Carol is a girl, which can also be read as Christine and Carol are girls. To demonstrate alternation, this compound statement is read as Christine is a girl or Carol is a girl. To represent this as a conditional, it is read as if Christine is a girl, then Carol is a girl. Lastly, by conditional, Christine is a girl if and only if Carol is a girl. Now that we know the difference between simple and compound statements, let us now move on with negation. Negation is represented by the symbol tilde. It is simply negating the statement. For example, the negation of a simple statement P is not P. The negation of compound statement P or Q is not P or Q. Notice that there is a parenthesis when negating the whole compound statement. Note that a parenthesis or bracket is used to mark the scope or domain of the negation to avoid confusion. That would be all for this module, friends. We're on to the next module. Our second lesson is about Sir Acuña's philosophical analysis, Unit 3, Module 3, entitled Truth Values of Compound Statements. Remember the three principles governing the truth values of statements discussed in our previous lessons? These are the principle of identity, principle of excluded middle, and principle of non-contradiction. In this part of our discussion, we will pursue the application of these principles in the analysis of the truth values of compound statements. First is the principle of identity. This states that if statement P is true, then P is true. Suppose the statements, kittens are young cats. It is true that kittens are young cats by definition, then it is true. Alternatively, if kittens are not young cats, then P is false. If P is false, then P is false. This principle states that statement P implies itself, thus making it always true, which is what we call a tautology. Moving on to our second principle, the principle of excluded middle. This principle states that any statement P can either be only true or false and nothing in between. This means that any premise and conclusion of a deductive argument can only be either true or false and does not have a third value. To explain, If statement P is true, then we know that the negation of statement is not P, which is false. A relationship called truth functional relation is explained by logicians as we know that P is stable over time as stated by the principle of identity. And principle of excluded middle states that this statement can only be true or false. To make things easier, the principle of excluded middle states that a statement can only be either true or false and not anything else. The last principle, the principle of non-contradiction, states that a statement cannot be true and false at the same time in the same respect. P can be true at one instance and false at another, but it cannot both be true and false at the same time. To use my former example, kittens are young cats, it cannot be stated as kittens are young cats and not young cats. Remember the discussion about negation that we had a while ago? We will now tackle the difference between negation and double negation. The truth value presented represents truth functional relationship, which means that if P is true, then not P is false, and if P is false, then not P is true. However, if P is denied twice, then it is called a double negation. For example, the statement kittens are young cats, when we negate it, this would be read as kittens are not young cats. And when we double negate it, this would be read as it is false that kittens are not young cats. This can be represented as tilde P or not P. Remember that when a statement is denied twice, then it applies its affirmation. Let us now move on to truth tables. In distinguishing how many rows of the truth table would be, we could use the formula 2 raised to n, where n is the number of statements. Suppose the statements P and Q. For the truth table of conjunction P and Q, the image attached shows the truth value table. Notice that the statement would only be true if P and Q are both true. For the truth table of alternation, P or Q, the image attached shows the truth value table. Notice that the statement would only be false if P and Q are both false. Thus, any remaining representation is considered true. For the truth table of conditional if P, then Q, the image attached shows the truth value table. The conditional is false only if the premise P is true and the conclusion Q is false. As stated as the logical form of deductive argument, a true premise cannot give us a false conclusion as the validity of the table is logically isomorphic. Lastly, for the truth value of biconditional, there must be an assertion of a necessary connection that P is true and a sufficient condition for the truth of P. The image attached shows the truth value table. Notice that a biconditional is only true under two conditions, when they are both true and both false. Thus, any combination results in a value of false. We have discussed negation and double negation earlier. Now, we will discuss how to negate compound statements. This is simple. We negate compound statements by using parentheses. For example, if we are going to negate the compound statement P or Q, it would be not P or Q, which is represented by this. So that's it for our second lesson, friends. Let us now dig in with our third lesson, which is the fourth module of Unit 3 entitled Representing Arguments. We are now on our third lesson, friends, the fourth module of Unit 3 in Sir Acuña's philosophical analysis. From the former lessons, we have learned that a statement can be represented whether it's simple or compound. In addition, an argument can also be represented. We represent arguments in order to reveal its logical structure and isolate it from its content. And the tip for you, my friends, we can determine the validity of an argument through its logical structure. Later on, I will share which form is valid and invalid. Let us consider this argument from Sir Acuña's book. Premise A: if we can represent statements, then we can represent arguments. Premise B: we can represent statements. And premise C: therefore, we can represent arguments. The first step in representing an argument is to represent simple and compound statements. Premise A is a compound statement, while premise B and C are simple statements. Suppose we represent the first premise A by the first letter of represent an argument, capital letters R and A respectively. And suppose we represent the conclusion indicator, therefore, with the logical convention of 3 dots, or this symbol. The next step is to represent the argument by revealing its logical structure. Once an argument reveals its structure, the logician can now inspect the logical form and determine if it is valid or invalid by extracting its truth table. Notice that by representing the argument, we have done away with the content. This shows that formal deductive logic is not interested in the content of the argument. Going back to the argument we had earlier, the vertical representation of the structure of the argument will look like this. So, this logical structure, first premise states a conditional, second premise affirms the antecedent of the conclusion, and the conclusion R is deduced from the two premises. The logical form of any argument with this logical structure is considered valid, because if we construct the truth table of the argument, it will not have a case where the premise set is true and the conclusion is false. Logicians call this as modus ponens, which means that the strength of a deductive argument rests solely on the logical form and not on the content of the argument. In fact, the content is irrelevant. Now that we know a valid argument form, let us now move on to invalid argument forms. To contrast with valid argument form, let us argue this way. Premise A: if we study logic, then we improve our reasoning power. Premise B: we improve our reasoning power. Premise C: therefore, we study logic. We can represent this argument in this way. The argument form presented of any argument and whatever the content is considered invalid. Logicians call this as the fallacy of affirming the consequent. This is an example of a formal fallacy. It affirmed the consequent and not the antecedent S, which made the argument invalid. Let us now consider another argument with a different logical structure. This example is called addition. Premise A: some arguments are valid. Premise B: some arguments are invalid. Premise C: therefore, some arguments are valid and some arguments are invalid. Let us use letter V for valid and letter I for invalid. The argument structure would be like this. If you will compare the argument structure of this argument with the argument structure of modus ponens, you will realize that any argument with the logical structure of modus ponens and addition has a logical form that is always valid whatever the content is. Here is the characteristic of all valid argument forms. There must be no case in which the premise set is true and the conclusion is false. Thus, if an argument form has a true premise set and a false conclusion, it is considered invalid. For the last part of this lesson, here is the logical form of all deductive arguments. Earlier, we have tackled this type of representation. You know that the premises of an argument, however numerous, are joined by conjunction. And if we're going to apply this to the argument attached, the result is a horizontal representation of the structure of the argument, which is this. The premise 1 and 2 are joined by conjunction and the therefore indicator. The 3 dots, which represent the conclusion indicator, was transformed into the symbol of the conditional, which is an arrow. This means that the main connective of the argument is conditional. This would also highlight the fact that the logical form of all deductive arguments follows the logical form of the conditional. The horizontal representation of the structure of the argument clearly shows the logical relationship between the premise set and the conclusion. They are joined by the conditional connective arrow. Consequently, it follows the logical structure of a conditional statement which we discussed earlier. To conclude, the validity of concepts confirm the truth table of a conditional statement. Namely, a conditional statement is false only when the antecedent is true and the consequent is false. Similarly, an argument form is only invalid if the premise is true and the conclusion is false. That's all that I got here, friends. Yana will be sharing with you the next modules. Bye!
Now let me discuss the basic deductive argument forms. In this module, it will sharpen your ability to discriminate between a valid and invalid argument. Suppose two statements are true. These statements may be any statements that are unrelated, but the only requirement is both statements must be true. Logician Fridge once said, that the referent of all true statements is true and the referent of all false statements is false. In this manner, we should be talking only of the truth and falsehood of argument, not about their meanings or empirical content. To start, Acuna used these two true statements. Amphibians are animals and birds have feathers, and used these two true statements as a representation of A and B. You can conjoin A and B, because conjoining two true statements preserves the truth value of the conjunction. The valid argument is technically called a conjunction. So now, as the conjoining two true statements preserve the truth value of the conjunction, separating their conjuncts preserve the truth values too. From conjunct A and B, you can separate their conjunct either A or B. Therefore, all arguments like this are valid, and this valid argument is called simplification. Next, suppose you know that two statements are true. Whales are mammals and snakes are reptiles. From these true statements, you can create an alternation. Either whales are mammals or snakes are reptiles. If you know two statements to be true, you are entitled to form an alternation and conjunct. From conjunction, you can validly infer any of the conjunct. From alternation, you cannot infer any of the alternates because any alternation is true even if only one of the alternates is true. Invalid argument structure is called subtracting an alternative. Suppose you know that FPJ is running for president is true, and that Ding is running for president is false. You can still form a valid argument, because again, alternation is true if only one of the alternates is true, but it is false if both alternates are false. This valid argument is called adding an alternative. Now suppose you know that a statement is true, you cannot add a conjunction because the statement you might add might be false. Suppose R is true, then it is an invalid argument. It is called adding a conjunct. Now let's talk about disjunctive syllogism. Detaching an alternative is valid when you know the alternation is true, not because both alternates are true. However, one of the other is false. Valid argument is often confused with disjunctive syllogism is called denying an alternative. It is invalid because even if you know that the statement FPJ is running for president is true, you cannot infer that the statement that Ding is running for president is false because it can still be true. On the other way around, another variation of the same invalid argument is if you know that Ding is running for president is true, you cannot infer that FPJ is running for president is false. As we finish to discuss the basic deductive argument forms, let us move on to the complex argument forms, which will provide you the technique for discriminating the more complicated argument involving conditionals. Let me introduce you to the modus ponens and modus tollens. In this part, we will focus on the more sophisticated argument that involves conditional. These arguments are more complicated than those arguments involving conjunction and alternation. To begin with, let us review the argument called modus ponens and the invalid argument called fallacy of affirming the consequent. From the argument structure, you can see the premise 2 affirms the antecedent, however, the reverse, which is affirming the consequent, is an invalid argument. On the other hand, let us discuss the modus tollens and denying the antecedent. Modus tollens is the counterpart of valid form of modus ponens. According to formal logicians, the valid form is when you deny the consequent, then you have the valid argument of modus tollens, or affirm the antecedent, and you get the valid argument of modus ponens. If you do the reverse, affirm the consequent or deny the antecedent, you create an invalid argument. If you deny the antecedent, the argument is invalid, called denying the antecedent. Remember that when you affirm the consequent and deny the antecedent, the result is an invalid argument. Detaching the consequent is an invalid argument. You cannot infer the consequent because the consequent and antecedent of a conjunction can be false, yet the conjunction can still be true. Hypothetical syllogism is another valid argument. Fallacy of misplaced middle, often confused with hypothetical syllogism, is another, more complicated, valid argument. Constructive dilemma is a valid argument. The logical form of constructive dilemma is a combination of two modus ponens. Destructive dilemma is a valid argument. The argument of the structure of destructive dilemma is a combination of two modest tollens. There are two fallacious forms of dilemmas that might appear valid but on closer inspection are not. They are called pseudo-dilemma. Pseudo-dilemma 1 denies the antecedent. This fallacy denies the antecedent of premise 1 and 2, and so it cannot conclude the denial of both the consequents. The argument denied the consequent, it could conclude by denying the antecedent. This valid form is called destructive dilemma and pseudo-dilemma 1. On the other hand, pseudo-dilemma 2 affirms the consequent. It is an invalid argument often confused with a valid one is pseudo-dilemma 2. It affirms the consequent of premise 2 and 3, and so it cannot affirm the antecedent. On the other hand, if it affirmed the antecedent, it could have concluded by affirming the consequent. Remember that either affirm the antecedent or deny the consequent of a conditional and you get a valid argument all the time. For the last part, let me discuss to you the truth table method. This will help you to apply the technique of determining the validity or invalidity of any argument form, and that technique is the truth table method. As you know that this modus ponens structure has a valid argument, it is to use the truth table method to conclusively demonstrate that the argument is valid. The argument form or logical form of an argument refers to its truth table. If the truth table of an argument does not have a case where the premise set is true and the conclusion is false, the argument form is valid. Now, let us discuss the truth table method and the steps to follow in order to use it properly. First, represent the argument in horizontal form like this. Second, count the number of simple statements in the argument. Now, you have to construct a table for all the possible substitution instances of the truth values of R and L. For instance, you have 3 statements R and L and Q. You'll have a table with 8 rows. These are all the possible substitution instances of truth values of an argument with 3 statements. I know that it will be a complex table with 4 statements. You will have 6 in rows. Then much more complex when you have 8 statements. It will result in 256 rows. Finally, after completing the table, assign the truth values to the statements in argument structure. In all possible substitution instances of the truth value of the statements of argument is valid, therefore it is tautology. Valid argument forms refer to the truth table. Valid or invalid specific arguments depend on specific truth values. Let us now consider the invalid form of affirming the consequent. Just the same with the steps, represent the logical structure argument in horizontal form. Then construct a table of substitution instance. And then assign the truth values to the argument. Notice that you have a case where the premise set is true and the conclusion is false. This argument form is invalid. In addition, the terms valid and invalid should be used in the argument form only. It is advised to use the terms valid or invalid to a specific argument. Now, let me introduce you to the shortcut method of using the truth table to determine whether an argument is valid or invalid. This is usually used when you have 3 or more statements, and this is called the falsification method. This method capitalizes on this by simply attempting to falsify the conclusion while demonstrating that the premise set is true. Let us consider this argument. Your intention is to falsify the conclusion while retaining the truth of the premise set like this. To do this, begin with your analysis from the conclusion. If P or R is false, this means that both P and R are also false. If the premise set is true, then this means that both alternation P or Q and Q or R are true. If P and R are false, the same values should be assigned to P and R in the premise set. Thus, you are left only with Q. Notice that whatever the value of Q, you have discovered a row where the premise set is true and the conclusion is false. Therefore, the argument form is invalid. A word of caution is appropriate here. When you have discovered a horizontal in which the premise set is true and the conclusion is false, you have conclusive evidence that the argument form is invalid. However, it does not necessarily mean that it is valid when you did not succeed in attempts of falsifying an argument. In such case, you must go about eliminating possible falsifying rows in a systematic way. This example will serve to illustrate this. The first step is to falsify the conclusion while retaining the truth of the premise set. Notice that if the conclusion is false, there are three possible combinations of truth values. Next is to assign the truth values of R and C in the first row, and then assign for L. Observe that the truth values in the box cannot be true. Therefore, you cannot maintain the truth of the premise set while retaining the falsity of the conclusion. You would think that the argument could not be falsified if you might jump into the conclusion that the argument form is valid. But remember that there are other combinations of truth values in the conclusion, considering that it is a conjunction. Notice that in the remaining combination of the truth values of R and C, you were able to falsify the conclusion while retaining the truth of the premise set. Therefore, the argument is invalid. And that ends our discussion for Module 2 to 7. Bye!